Hey everybody, good morning. So I want to apologize for that last round of uploading videos. That was horrible. As you've seen, I had to break it into two halves to get that to work. For some reason it kept on crashing on me, and it was just because the video was too big. So I will try to spend less time of me talking and focus strictly on the work that we have to do. So moving into this next section, I think I told you before that this chapter is really about rotating things around a line and trying to figure out the volume of that solid that we just got. Let me focus in on the book here. So the idea is that you take some equation, which would be this black line right here, and what you do is you rotate that around the x-axis and it creates a shape that looks like this. Now, remember how when we found area we were adding up a bunch of rectangles? Well, this rectangle now sort of represents the radius of, we're going to call it a disk. Okay? Kind of like in track and field you have the discus. It's like that. And instead of adding a bunch of rectangles together, what we're now doing is we're going to add a bunch of disks together. And so the goal is to figure out a way to get the volume of each of these disks and then add those up. And so just like when we add a whole bunch of rectangles, we do that with an integral, we're going to add a whole bunch of disks and do that with an integral as well. And it's really not too bad. Let's take a look. One more thing. Remember how when we were doing our area between two curves, sometimes we had sideways rectangles? Well, sometimes we're going to wrap this around a vertical line, and what we get is sideways disks. And so when that happens, we're going to call this the thickness. We have to think of that as our dy value. When we wrap around a horizontal line, then our radius runs this way, and so the thickness of that disk, that runs in the x direction, the same as the x-axis. We're going to call that a dx. So disks that are perpendicular to the x-axis, those are going to have dx's with them. You know, again, picture this being wrapped around a disk that's perpendicular to the y-axis. We're going to have to call that thickness dy. All right, so we've got a problem here. And it says to find the volume of a solid when y equals x squared, so just a standard parabola, on the interval 0 to 2 is rotated about the x-axis. Well, here's what that graph would look like. Here's my vertex. If I go over 1, I got to go up 1 squared, which is 1. If I go over 2 units, 2 squared is 4. So 2, 3, 4. And so what I want to do is I want to take that curve on the interval 0 to 2 and rotate it about the x-axis. I don't know why they use the word about instead of around, but that's what our book uses. So when I do that, if I rotate this around, what I'm going to get is a shape that looks like this. So I don't know if you can visualize that, but it almost looks like a funnel that's sideways. And this is a solid figure. It's solid all the way through. And what we want to do is we want to find the volume of it. And so if you can go back and kind of in your mind get the picture from our book of all those disks that are side by side, here's one of those disks. And what I'm going to do is I'm going to have a bunch of those disks stacked side by side from 0 to 2. It'd be a really small disk up here, and the largest one would be here at the end. And so what I want to do is I want to find an equation for the volume of one of these and then add them all up from 0 to 2. Well, if you think about that, that's really just a cylinder, right? If I had a cylinder like this, I would say that the volume of this is just base times height, which the base is going to be a circle. That's pi r squared times the height. Here's our height. We've got a radius right here. Okay, but what we're doing is we're going to make these discs very, very small, very narrow, so that the height is pretty close to 0. And so I want that to become, now I know this is running up and down, that should be a dh, but picture this whole thing sideways. That's going to become my dx right there. That's the thickness of this particular disc. So now all I need to do is just find the area of the circle, which is pi r squared times dx, and add those all up from 0 to 2. So my formula for that is just going to be this, the integral from 0 to 2 of pi r squared dx. And that equation would get us the volume of this solid. So the question now is, well, what's the radius going to be? The radius is really just the distance from here to here. It's just a y value. If I go from the x-axis up to this point, the radius of this circle is just that y coordinate. And so I know right here y is equal to x squared. So if I put an x squared in here for the radius, then I've got everything in terms of x. These values, my interval, which are x values. I've got an x expression here, and then dx, which means I want everything to be with respect to x. So if I change this integral to this, I'll move the pi to the outside since it's just a number. My radius is x squared, and I have to square that, and then dx. So I've got pi times the integral 0 to 2 of x to the 4th dx. That's going to give me the volume of that solid. So the actual integral isn't very difficult at all. That's the easy part. It's getting it set up. So this is going to be pi times x to the 5th over 5. We're going to evaluate that from 0 to 2. And so if I plug that 2 in, I'm going to get 2 to the 5th power, which is 32 fifths, minus what I get when I plug in a 0. Still multiplying by pi. So my final answer here is going to be 32 pi over 5. That would be an exact answer. If I put it in the calculator, I would get the decimal equivalent. And since we're talking about volume now, we're now talking about cubic units. The number of cubes to fill this shape up. All right, so let's do the same problem, except this time let's rotate about the y-axis. So we're still finding the volume of a solid when y equals x squared on the interval 0 to 2 is rotated about the y-axis. So we're going to rotate this equation around the y-axis. And so when I do that, over on this side I would just get the other half of that parabola. If I'm rotating this around, what I get is a picture that this time looks more like a bowl. And since I rotate it around the y-axis, now my discs are going to stack vertically with the smallest one down here, the largest one up here. So here would be one of those discs. And you guys, I think this is really important that we draw this picture. You know, without drawing the picture, if you just try and sit there and figure everything out in your head, that's not an easy thing to do. I don't think I would be very good at that. And I need to see the picture so that I have all the information down and I can see exactly what I'm doing. So this is why we had to talk about the volume with sideways rectangles. The area between two curves with sideways rectangles is because we're going to get discs like this. And so when I look at this, my first thought is the thickness of this disc is running up and down. That's in the y direction. So I need to think of this as dy, which means everything in this integral needs to be in terms of y. I'm still going to do the same thing. I'm still going to start with the volume equals the integral from a to b of pi r squared. It's just this time it's going to be dy instead of dx. So the first thing I want to think to myself is, as I stack these discs on top of each other, smallest ones at the bottom, largest ones at the top, I'm stacking those from what to what? Think about that for a second. Because what we're trying to do is find the a and the b values. These discs would stack from what to what? Well, if I'm on the interval 0 to 2, the lowest point is at x equals 0. If I plug it in, y is going to equal 0. So this would be the integral from 0 to, when x equals 2. Plug that in, 2 squared is 4. And so our top disk is going to be at y equals 4. So we're stacking these things from 0 all the way up to 4 on the y-axis. Still going to have pi. It's a number. I'll move it to the outside. We'll do that every single time. My question here is, what's the radius? I can't put in x squared because I need everything in terms of y. So what I need to do is I need to take this equation, y equals x squared. I need to think to myself that the radius starts right here on the y-axis and goes out to some point on this curve. All right, now this part's important. The radius starts right here on the y-axis and goes out to this point. So I have to think to myself, what's the length of that line? And not only that, but as it moves, so as my discs come down here, the radius is going to be smaller than it is up here. So I have to have an expression that controls that radius as my y values move from 0 to 4. So when I look at this, if it starts right here and goes out to some point on this parabola, then really whatever that x coordinate is, that's going to be the radius. So I just need to solve this for x, and then that's my radius in terms of y values. So we'll just say that x equals the square root of y, and now I just need to put that in right here. So the square root of y squared is just y, and there's the integral that we have to solve. Now I know I told you guys you can use your calculator in this chapter. I feel like using my calculator to solve this integral is kind of like doing 2 plus 4 on the calculator. This is probably something we should do on our own. So this would be y squared over 2. We're going to evaluate that from 0 to 4, and then multiply by pi. So if I plug in a 4, 4 squared is going to be 16. 16 divided by 2 is 8. So I've got pi times 8 minus what I get when I plug in a 0. That's just 0. And so my answer is 8 pi, not square units, cubic units. There it is. All right, so I'm going to let you guys try this one on your own. We want to find the volume. when this equation, y equals the square root of x minus 1, is rotated about the x-axis on the interval 1, 5. Start with a picture, then set up your integral, and go ahead and solve that. You guys give it a shot. All right, so if we think back to pre-calculus, when you graph square roots, we know what a square root function looks like. This has been shifted to the right 1 unit. So there it is. And we're going to rotate that about the x-axis. So as I rotate this around, we'll have the same shape down here. My solid figure would look something like this. And what I need to do is, I only have to draw one of these discs. I don't have to draw multiple ones. So here's the disc. I'm always going to draw this with a little bit of thickness to it. And I can see that that thickness runs in the x direction. So that right there is going to be dx. That means when I set up my integral, I want everything to be in terms of x. So we would stack these discs side by side from 1 to 5. I then want pi r squared, so the area of this circle right here. And so I need to know what the radius is. Now, when we think of the radius, we have to think of the radius as going from the axis of rotation, whatever you're rotating around, up to the original curve. So up to a point right here. That's going to be the radius. And so if I think about that, it's just a y value. And y is equal to the square root of x minus 1. So that's what I want in my equation right there. When I square that square root, I come right back to just x minus 1. So I've got pi times the integral from 1 to 5 of x minus 1. Don't forget your parentheses here. With respect to x. And again, I think this is a pretty easy integral to solve. We don't need our calculator to do this. You can if you want, but I think we probably should do as many of these as we can without the calculator, as a way just to review and make sure we're not forgetting some of the simple things about integrals. That's really important as we go through this. All right, so I've got pi times x squared over 2 minus x. We're going to evaluate that from 1 to 5. So if I put in a 5 first, I get 25 squared over 2, or 5 squared, which is 25, over 2, minus 5, minus what I get when I plug a 1 in, which would be 1/2 minus 1. And so let's see, this would be 12.5 minus 5, that would be 7.5, minus 1/2 minus 1, that would be a negative 1/2. So I'm going to subtract a negative 1/2, that means I'll add that. 7.5 plus a half, that's just 8. So I got 8 pi cubic units. So let's try the same problem, but this time we're going to rotate around the y-axis. All right, so if I'm rotating this curve right here around the y-axis, that means when it rotates over to this side, it's going to look like this. I'll have kind of a circular shape up here, circular shape down here. I won't be able to see this, so I'll make that as a dotted line. So it almost looks like a tornado or a hurricane, coming down and touching ground, something like that. And so we're trying to find the volume of this. So again, I'm going to draw one of these discs in here. See, my thickness is running up and down, so that means that's got to be a dy value. So when I set up my integral, I want everything in terms of y. I'm going to just start putting the pi on the outside because it's always going to be a number. It can always get moved to the outside. So I have to figure out where these disks are stacking up to. They're starting at 0 and going up to whatever we get when x equals 5. So if I plug in a 5, 5 minus 1 is 4. The square root of that's 2. So these are going to go as high as y equals 2. So our integral will go from 0 to 2. And so now when you look at this, my radius, boy, I wish I had a different color here to do this, but I don't. My radius starts here, it goes out to some point. That's going to be an x value, but I need everything to be in terms of y. So I need to go back to this equation and solve that for x. So if I square both sides, I get y squared equals x minus 1. I'll then move the 1 to the other side and I get y squared plus 1 equals x. There's our radius. So I want y squared plus 1 squared. Remember, it's pi r squared. So that means my integral is now the integral from 0 to 2. If I square this, I get y to the 4th. Multiply the 2 and double it, plus 2y squared plus 1 dy. And so now if I solve that integral, I've got y to the 5th over 5 plus 2y cubed over 3 plus y, and we're going to evaluate that from 0 to 2 in terms of, and then times pi. So this starts to become kind of a lot. So maybe this was a calculator problem, maybe not. I mean, it's not too bad. I've got pi times, when I plug a 2 in, I get 32 fifths plus, this will be 8 times 2, that's 16 thirds plus 2. Minus what I get when I plug in a 0, that'll just be 0. And so I can just add those fractions on the calculator. So I've got 32 divided by 5 plus 16 divided by 3 plus 2. That's 206 over 15. So that would be 206 pi over 15 cubic units. There it is. All right, so that's all we have for today. Here's our assignment. We're going to call this number C2, page 463. We're going to do 1 to 4 and 7 to 10. So you guys take care. I'll see you next Tuesday. That will be my next video. I know it's spring break, but look, we're all on a break, and I think we just need to try and do the best we can. So I will still put out 2 videos. If for some reason your family's going somewhere, which I know a lot of us aren't, we're staying home, but you can access this from anywhere, or you can just look at it when you get back. So take care. You guys be safe, and see you on Tuesday.